I will talk about the recent work with Thomas Strobl here about the twisted Poisson sigma model. So first, I would like to talk about the motivation and what we want to do. This is we're going to construct BV and BFV formalism with H-twisted Poisson sigma model. The purpose is one purpose is to understand the geometry of the twisted Poisson structure and the more generally higher Dirac structure and the real algebroid and so on, the higher structure in terms of the quantum field theory and the quantization of the quantum field theory. And another motivation is a kind of generalization of the AKSZ, so-called AKSZ Sigma model, which is the Sigma model related to the so-called derived geometry and the graded manifold. So, okay. I will talk about this is a plan of talk. First, I explain twisted Poisson sigma model, and next we consider BV formalism of this model, and some reformulation are a kind of reformulation of this model to AKSZ Sigma model. And if there is a time I want to explain BFV formalism. Okay. First, I'd like to explain twisted Poisson sigma model, so-called H-twisted or twisted. Twisted Poisson structure is this one. Let M be a smooth manifold, and pi is a bivector, and H is a closed free form. If I and H satisfy this equation identity, this is called twisted Poisson structure. And this bracket is a so-called Schouten bracket on the multivector field. So this is some pairing of the T time Tm pairing. If H equals 0, this is the Poisson structure, nothing but Poisson structure. And but if H is not 0, this is generalized. So, and one note is that this is an example of so-called Dirac structure on Tm plus T star M. And this is one example of Dirac structure. And another important fact is that we can define the real algebroid from this structure. What is this one? This is a definition of real algebroid. Maybe some people know very well. The algebroid is a vector bundle with two operations. One operation is a row. It is the so-called anchor map, bundle map from E to T star M, Tm, vector bundle, and the bracket is a bracket, which satisfies the so-called Leibniz rule, this equation. In this case, this is called real algebroid. So in our case, if we define the anchor map like this, where here pi sharp is a map from cotangent bundle to tangent bundle induced from y vector, and the bracket on the space of one form is defined as follows, which is a kind of the Lie bracket, so-called Kodur bracket, a kind of generalization of the Kodur bracket. So if we define the operation like this, from twisted Poisson structure, we obtain real algebroid structure on T star M. Next, we define twisted Poisson sigma model. Sigma model means some physical model from some mapping space of two manifolds. First, we consider twisted Poisson manifold M, and we introduce another manifold N. This is a three-dimensional manifold with two-dimensional boundary sigma. So-called field is a coordinate on the mapping space. In the physical, it is called fields. They are called fields. The X is a map from N to M, and A is a one form. Sigma, this two-dimensional boundary manifold, with taking value of the pullback of the T star M. Sigma is a coordinate on sigma. And this is two elements are regarded as a local coordinate of this mapping space. So the classical action, we consider a kind of mechanics. Classical action is defined as follows. This is the first two terms are the integration on sigma ADX plus this is the bivector. Then the final term is the integration on three-dimensional manifold. This is so-called West-dimensional term. It's a pullback of the H. And if H is equal to 0, this model is called the Poisson sigma model. Yeah, this is the Poisson sigma model. So this model is a kind of generalization of the Poisson sigma model written by the final decimal term H. The equation of motion, we use equation of motion, but we have two equations of motion, but the important thing is the first one, Fi, equation of motion, this one. Yeah, it is obtained from the normal variational principle of analytical mechanics from this here. Why this model is called the twisted Poisson sigma model. So we explain briefly the consistency condition of this model. In order to explain, we consider Hamiltonian formalism. In this case, we take two-dimensional sigma like this, or the R times S1 or the torus. It is kind of the physical or mathematical setting. Maybe mathematical setting or the mathematical setting, we should take compact manifold T2 and so on. But physically, maybe we can take the infinite time. So time should be minus infinity to infinity. So maybe this one is for physical setting. We take first we choose canonical conjugate moment of pi as a spatial component of the A. This is not important. Not to, usually the canonical conjugate moment should be Darboux coordinate. Consist of constructed Darboux coordinate, but we in this case the simplex form is like this. It is not the Darboux coordinate, but it is convenient choosing of coordinate. If h equals 0, this coordinate is reduced to Darboux coordinate. That this is a Poisson bracket induced from this post-simplex structure. So we consider Hamiltonian formalism. So this is a Hamiltonian, where J is a spatial component of the equation of motion explained before. This is a spatial component. So this equal to 0 is equation of motion, a part of equation of motion. So this should be consistent with the Poisson bracket. So we obtain this theorem. If pi and h is a twisted Poisson structure, Ji, this one, consists of closed Lie algebra. So this one, we can prove that we can easily compute like this, this equation. So that it is equal to 0 condition is consistent with the Poisson bracket. Where the Fijk is a structural function of Lie algebra induced from twisted Poisson structure, I explained the part. This one. We can compute the structure function, not constant, the function, the function of the base manifold X. This Lie bracket is has a structural function. This is the structural function of the Fijk, which appeared here. This is concretely the definition of this, but it's the Fijk. So this mechanics is consistent with this Poisson structure. Ji is called twisted first class constraint. So we want to explain, go to the BV formalism, but anyway, the first class constraint, from first class constraint we can construct the gauge transformation in the Lagrangian formalism. This gauge transformation is here, this one. Then the important thing is the gauge transformation AI. The first two terms is a normal generalization of the gauge transformation of the connection of Lie group vector band. But we need third term. This is the proportional to the Fi. Fi is the left-hand side of the equation of motion. This one. Why this one? What is this term? So, in order to consider the interpretation, the meaning of this term, we did the meaning of the third term, this one, becomes clear by introducing target space connection. So we introduce target space connection. The interesting thing is this action functional of twisted Poisson sigma model is also invariant under the target space. Covariant gauge transformation with the connection. This one, this red line, third term, if we replace third term to this one, this action functional is invariant. So this is also gauge transformation of this model. The third term, gamma is a crystal symbol of the affine connection on the target space. This one. But the important thing is the affine connection has torsion. This is a symmetric. The gamma circle is a symmetric part of the affine connection, but we have anti-symmetric part. This is torsion term. So this interpretation of this term is torsion of the target space connection. So this is a more geometrical expression of the gauge transformation, which is in some sense, target space covariant, the gauge transformation. So the H term, if H is called non-zero, we introduce, the torsion term is introduced. Next we consider the normal procedure, physical procedure to construct BV formalism, to construct BV and the action functional BV formalism. In order to construct BV formalism, first we consider so-called BRST transformation. BRST transformation is defined by shifting by this gauge parameter epsilon to the so-called ghost field. And this is odd ghost field, this is even. So we shift degree, only we shift the degree that this is obtained the BRC transformation. Usually BRC transformation, square of BRC transformation is in 0. If we define the BRC transformation of C like this, this is the same as normal BRC transformation of the Lie group case, but this Fijk is not constant. We obtain square and S square on Xi and Ci is equal to 0, but the AI on AI S square is not 0. So first result, our first result is this one, not equal to 0, but this one. What is S? This is proportional to Fj equations motion, but the coefficient Si. What is the coefficient? Is we have coefficient Sij(Kl). What is this tensor? This tensor is so-called basic curvature on the Lie algebra connection. This is defined like this. That's what is this one? R is a normal curvature of the this our affine connection. This is curvature, and rho is a anchor map of our Lie algebra, right? This is the anchor map is also regarded the section of T star M, the Tm. The T, large T is so-called E torsion of the Lie algebra covariant derivative. It is defined like this. Other than torsion and curvature, on Lie, we can define so-called E torsion and Lie curvature on Lie algebra connection. This is E connection, not connection, not torsion, E torsion. Then, and S tensor is defined like this. This tensor is, in some sense, like E curvature of the E torsion. It is some kind of the curvature-like the object in the Lie algebroid connection. So this S tensor appeared in the right-hand side of the square AI. This is the very geometric result of the BFC transformation. So if S square A equal not equal to 0, we need BV formalism. So BV formalism procedure is as follows. First, we consider BRC field which appears in BRC formalism XAC, and we consider shifted cotangent bundle, shifted -1 shifted cotangent bundle. This is the space of BV formulation fields of in PV formulation. This is the cotangent bundle. So naturally we can define canonical simplified form like this. The X plus coordinated canonical cotangent conjugate canonical conjugate field. So this is this model has 2 degree. F is a form degree on the base world sheet sigma. This is the sigma model is a theory on mapping space of sigma to M. This is the degree on sigma. This is the degree of the shifted cotangent bundle target space, the Gauss number. So this is the usual assignment in the BV formalism. So finally we want to construct BV functional to satisfying this equation, the classical master equation. And this is this bracket is a graded Poisson bracket induced from this BV simplex form. So this is odd bracket, and this if SVV, this bracket means that SVV is defined, give the homological vector field as a homological function. So this is the Hamiltonian for the Hamiltonian vector field. This Hamiltonian vector field induced from SVV is homological. That this is squared to 0. Now we want to construct SVV function on mapping space. The BV procedure is as follows. BV functional determined by the addition with a contribution to minimal PRC extension classical action. That first we consider expand the like this. The expansion is order of anti-field. Usually the usual BV in usual BV formalism, we expand the order of the anti-ghost number, but now we expand the BV action by order of anti-field. This is like the AKSZ type Sigma model procedure. So then the first S0 is we take S0 as we take classical action as S0, and S1 is also fixed like this. This is the normal formula in BV formalism. This is already fixed to obtain BV action. Then the problem is that from the second term, S2, third term, and fourth term, and so on. Our result is as follows. In the twisted Poisson Sigma model, we the SBV terminate the third term, S2. This is already fixed. So the problem is to determine S2. S2 is like this one. S2 is proportional to the S tensor. This is S tensor, a basic curvature, and this is some coordinate anti-ghost. So this is a very geometrical result. So finally we can prove that this satisfies the classical master equation by using some identity of the real algebroid and the curvature and the geometrical identity. For example, S1, S2, bracket of S1, S2 must be equal to 0. This is proved from the Bianchi identity of the basic curvature, like this. This is essentially this is the E covariant derivative of S is and some product of T torsion, E torsion, and S, and some the alternation in the anti-symmetrization and so on equal to 0. It is the kind of the Bianchi identity. So from Bianchi identity we can prove this one, and finally we can prove classical Buster equation like this. So the purely geometrically we obtain the BV action function like this. This is And each term is written by the geometrical quantity, for example, pi and h, and Fijk is the structure function of real algebroid, and gamma is a connection, target space connection, and this is a basic curvature. So maybe we obtain some geometrical construction of the BV action of the twisted Poisson sigma. So, right. We can rewrite manifestly covariant form like this. So by taking covariant coordinate. Next step. Next, we want to discuss the so-called AKSZ-like formulation of this model. We constructed BV action functional, so we can rewrite this action functional in terms of AKSZ type super graded manifold formulation. In order to consider this formulation, we need to take gamma symmetric part of gamma, the connection equal to 0, and because the Poisson, in the Poisson sigma model, this AKSZ construction works in this case. So we take the gamma symmetric part equal to 0, so the torsion part, only torsion part remained. So left. So we obtained a rather complicated the BV action from this action. So we want to consider this the AKSZ sigma model, a kind of AKSZ type sigma model of this BV action. So the first, in the AKSZ type sigma model, first we consider the space of mapping space of the two graded manifold. Here, in this case, this is the same as the case of Poisson sigma model. That this is the mapping space is the tangent, shifted tangent bundle of the sigma to shifted tangent bundle, cotangent bundle of target space M, this one, mapping space. The local coordinate is X, bold X and bold A. This is the combining of the each the fields in the normal BV formalism like this. This is the same as Poisson, the case of Poisson sigma model. This is the total degree is defined by the sum of the two degree, Gauss number and the form degree. And BV simplistic form, we can define natural Gradius canonical simplistic form, this mapping space, but this is the same as the original, the BV simplistic form, equivalent to the original simplistic form, shifted simplistic form like this. This is the equivalent to original one. This is the mapping space, and this graded simplistic form is the same as the original AKSZ construction of the Poisson sigma model. Finally, we have to construct the homological function SBV in the AKSZ procedure, but normal AKSZ procedure doesn't work in this model. In the normal AKSZ procedure, action function SBV is simply obtained from the classical action by replacing the normal field to superfield on the graded manifold, mapping space of graded manifold, and replace derivative to super derivative. All the things, if all the things are replaced to derivative super space, so we easily obtain the classical BV action. This is the AKSZ procedure, but this procedure doesn't work in this H is not case. Not the case H is non-zero case because this is the simple replacement. But the classical matter, we can compute the classical matter left-hand side of this bracket. It is not zero. We can easily prove that it is not zero, so this is not correct classical BV action satisfying classical matter equation. The solution, correct classical matter equation like this. This is our next result. This is naive. The first line is naive, the BV action. This is this one. And we need add these terms for the correct classical BV action. And here the epsilon is so-called Euler vector field defined like this. At sigma mu is a super coordinate on the T1 sigma, the super direction, to coordinate on super direction of this parallel sheet sigma and sigma. This remaining terms, all the remaining terms contain this Euler vector field. So we can easily prove that by expanding, and we can easily prove this satisfied classical matter equation by expanding this A and X to the component field, and this one is equivalent to the BV action functional SBV obtained in the previous section. So this is the correct one. So we can, from this example, we can propose the so-called generalized AKSZ Sigma model, a kind of generalization. This is not so definite result, but we can propose. First we consider D dimensional manifold sigma, and M is some target graded manifold. Then we consider some mapping space, this one. This mapping space, then the M is has a target space. M has the BV simplex form. And we assume the BV simplex form degree -1 on mapping space. The BV action is obtained by expanding like this. Where SBVK is the case order part of Euler vector epsilon. If the SBV0 is simply replacement of the fields to superfield in the classical action, this is the simple replacement of the classical action phase. This is the normal. If the SBVK equals 0 for the higher term, it is a normal AKSZ formulation, but it is not the general case. In fact, in our case, the twisted Poisson sigma model case, the S1 and S2 exists. So we can propose generalized AKSZ Sigma model type. But it is not so established in mathematically, so we need some more analysis for this model. Okay, there is no time to explain. So we summarize our result. We have constructed the BV formalism twisted Poisson sigma model. And we analyze the BFV and BV formalism by introducing target space connection at some geometric structure. We analyze the geometric structure of BFV and BV formalism by introducing target space connection. They are described by geometry of the Lie algebroid. And the superfield formulation is a kind of generalization of the AKSZ Sigma models. And yeah, we also constructed the BFV formalism twisted Poisson sigma model. And other work, further work, other work is we also applied this model, the formula of so-called Grigoriev Damgaard. This formula is the formula to construct the BV action functional, Lagrangian BV action functional from the Hamiltonian-BFV formalism. If we applied this Grigoriev Damgaard formulation, we need some improvement to obtain the covariant action. This is the other work. And the further outlook is as follows. Of course, we need some. This is the quantization of this model is very important, interesting because this the quantization of Poisson sigma model gives the deformation quantization formula of the Quantization. So we can obtain a generalization of the Quantization formula by quantization of this model. And another interesting thing is generalization to more, for example, to Dirac structure, more general higher structure. A twisted Poisson sigma model is an example of twisted Dirac structure. So more general model, we can consider more general model, for example, a Dirac sigma model and so on. And the other ambiguous thing is we need some, there is a possibility to generalize AKSZ Sigma model. I'm not sure. So this is maybe we can analyze such a generalization. Okay, thank you. Thank you very much for attention.
Yeah, thank you very much for the talk and for staying perfectly in time. So we have time for questions. Yeah. Are there questions here from the lecture hall audience?
So as a question from non-specialist, maybe also to Thomas. So why this procedure fails to construct BV action? So when you just replace fields with superfields, so why it doesn't work for this H-deformed module? So what's the abstraction? I mean, can you qualify that? And maybe there is some general procedure. So whenever it fails, this simple recipe, there is some general procedure how to solve the problem. Thank you.
As a in the normal, the BV formalism is more general than AKSZ. AKSZ Sigma model is a special part or special model among all the BV formalism. Right? It's only the very beautiful structure. There is only special case of all the BV formalism. There's no reason to the work, the AKSZ Sigma procedure work. And maybe the AKSZ Sigma model are almost classified among all the BV formalism. So this twisted Poisson Sigma model is the simplest generalization of the AKSS procedure doesn't work. We can, so example, why? It is because the so-called West-Domino term breaks some good structure for this one. This one breaks the good structure of AKSZ Sigma model. This is the reason, but it is not so definite answer, right? Yeah, almost the AKSZ Sigma model is classified. If there's H equals 0, this works. This is one of the simplest, the two-dimensional AKSZ Sigma model. This is a Poisson Sigma model. All the AKSZ Sigma model is our Poisson Sigma model. In AKSZ Sigma model in 2 dimensions is the Poisson Sigma model. So this term breaks this this example. So AKSS procedure doesn't work. Okay, it is a good answer.
Okay, thank you very much.
Yeah.
Is there was a further question over there?
Thank you. Am I correct that in that generalized AKSZ superfield formulation, that it does not involve any bulk integrals over n? Because this is kind of an extra data here, that the manifold, that sigma bounds a manifold, n. So in the way you wrote down the very end, you wrote down this.
It is this is, we need much, in the general theory, we only consider simplest case. We consider simplest case. We consider only the integration on sigma, not n. And if the h is exact, and this integration reduced to the integration on sigma, right? So we consider only simplest case. We need generalization to introduce non-exact H case. We only consider, in this case, we only consider the twisted Sigma in this case, in this example. So, yeah.
But if H is exact, you can gauge it away, can't you? And you can reduce it to an ordinary Poisson Sigma model for the gauged Poisson.
No, and the H is exactly due to the B, the integration of two form on sigma. It's this time reduced to integration on the two form sigma.
Okay,
H equals dB equal H equals dB, the integration of dB, B.
No, that's clear. I'm just asking, wouldn't that be equivalent to the Poisson sigma model for the Poisson structure gauged by B, if H is dB?
H equal.
Yeah, if H is equal to dB, then your extra term would be the integral over sigma of B. So, but wouldn't that be equivalent?
Yeah, sigma of B.
To a Poisson sigma model, without any three form, for another Poisson structure, which you obtain from pi by gauge transformation given by B.
Yeah. We can change the Poisson pi to some Poisson structure by gauge transform. Gauge transformation means the transform by changing of some changing of the combination of pi and B. Yeah, right. So we can change to Poisson structure.
Okay.
Mathematically. So
Thank you.
yeah.
Okay,
You
thank
are
you.
right.